then the whole situation becomes very relaxed. Okay? And I'm hoping that the learning process can be a fun process and also a very nature process, but not sort of remembering a lot of things. All right, and there's a trick for you to prepare slides. And the trick is that you want to put a lot of cartoon, you want to put a lot of drawing into the slides, so that you don't go through formulas and text in the presentation. Okay. So try to put a lot of image, cartoon, drawing into your presentation, and make it attractive and also intuitively easier for people to absorb it. All right. So this page is not a good slides, but this is so important that I need to show the Maxwell equations, because everything is based on Maxwell equations. And then in addition to Maxwell equations, we have the very important two equations. One is so-called Lorentz force equation, and the second one is the equation of continuity. Lorentz force equation tells you human experience. Okay, human experience is that you have a force you can experience, and then you start to understand why and understand the deeper in the content. Okay. So Lorentz force equation tells you have electric force, you have magnetic force. And what is peculiar and also interesting is that for a magnetic force, the charge need to move to experience the force. So if I'm a charge in space and I'm stationary, if I experience a force, it must be an electric field in space. If I don't feel a force, but I start to move, and then I got pushed, then it must be a magnetic force. Okay, so this is what Lorentz force tells you. Then equation of continuity tells you the conservation of charge. Okay, it's a conservation of charge. So it tells you that in the closed surface, if you measure some current, there must be some charge going through this surface. So this is the concept of the conservation of charge, and we call this equation of continuity. Okay. So all those equations explain all the known electromagnetic phenomena in nature. Okay. So this is the a set of all the formulas you want to understand from this electromagnetic theory. And then if it's an ohmic material, well, we deal with a lot of ohmic materials. For example, a piece of wire, then if you run current through, then the current density is going to be linearly proportional to the electric field. And we call this the ohmic material, the relationship of ohmic law between current and electric field. Okay? But if it's not an ohmic material, for example, if you have a current propagating or charge propagating in vacuum, it's not going to follow this formula. Okay? It's going to follow the F equal to a kind of relationship. So you have electric field proportional to the differentiation of the velocity with respect to time. So in fact, this is going to be proportional to the GA differentiation of current over time. If you have the charge propagating in free space, okay, and the linear relationship between J and E is only valid for ohmic material because of collision of the electron in material. You have linear relationship between J and E. So this means that you have dissipation of energy in the material. Okay, but without energy dissipation in the material, then you have sort of different kinds of relationship between the electric field and also the current. Okay. All right, so if you have a material nearby, you could modify the electric field. And that is because you induce dipole inside such a material. You polarize the material. Okay. Suppose you have some charge here. Then you will sort of polarize the material to have a negative surface here, positive surface here. So you induce some internal field here to offset the external field. Okay. So the net result is that if you have an external field generated by, for example, by this positive charge, the electric field is going to go into this direction. But then the internal field is going to go along this direction, okay, to cancel this external field. So the net result is that the electric field inside this material is reduced, okay, because of this polarization effect. Okay. So you end up having a reduced electric field. Well, this D is related to a charge. Remember Gauss law. Right? Gauss law tells you that this D is proportional to the charge. Remember this? So if you have a charge, it's going to produce the electric flux density. Given a charge, then you produce electric flux density. But the polarization of the material is going to reduce the electric field by a factor of this permittivity. Okay, by a factor of this permittivity. If you can see that if you have a positive charge, then you have the electric field going this direction. But then you have a plus dipole charge here and negative dipole charge here. You produce an electric field along this direction. And then they cancel each other to some extent. So the net electric field inside is reduced by this factor called permittivity. Okay, so this is sort of intuitively acceptable to you, right? Because you sort of polarize the material. And when you do the presentation, you want to put those cartoon, those kind of drawing in your slides, so that people can capture the concept easily. All right. So in vacuum, apparently the relative permittivity is equal to 1, but in the material, you have a reduction of the electric field by this factor. All right. So, but magnetic field is different. Magnetic field is that from Ampere's law, if you look at this Ampere's law, it tells you that, well, without this, let's drop this term for now. If you have current, you can produce magnetic field. Okay. So H is the proportional to the electric field. So if you put a material, magnetic material nearby, and then if you have some magnetic field, you reorient the magnet. You did this experiment before, that if you have some coil, then you produce some magnetic field, and then if you have a small magnet, it's going to reorient those small magnets such that the net effect is that the magnetic flux density is increased. Okay. For this case, the electric field is reduced by this because you depolarize the material. But for magnetic flux density, the effect is just the opposite. You reorient this small magnetic dipole so that all the magnetic flux density will add up to an even stronger value. Okay. So it turns out that this magnetic flux density is going to be multiplied with this relative permeability. And this relative permeability can be very big if you are dealing with the ferromagnetic material. Okay. And so this is sort of electric field and magnetic field. The concept of electric field and magnetic field are sort of complementary to each other. So it's there's I would say very beautiful symmetry in nature when you deal with magnetic field and electric field. Okay. Any question about this? Okay. So when you have a material nearby, the electric field is modified, or the magnetic flux density is modified. Okay. And D is created to be proportional to the charge. H is created to be proportional to the current. So you see the symmetry in this discussion. Okay. Well, in human nature, in nature, what human experience is this. What human beings experience is electric field and magnetic flux density. So these two variables are generic. Okay. What is invented in the theory is E, and that is proportional to the charge. And what is invented in the theory is H, that is proportional to the current. And those are the mathematical constructions. Okay. But in our experience, we deal with E and B. In our applications, we deal with E and B. Okay. But mathematically, we create D and H, and that D proportional to the charge, and H proportional to the current. And then we can come back to calculate this E and B. So you see that the purpose is to calculate this E. The purpose is to calculate this B nearby a material. So this is the sort of construction of the electromagnetic theory. Okay. But eventually we want to come back to E and B, so that that is in our applications. Okay. Well, a simple medium is a linear, isotropic, and non-dispersive material. Okay. So we focus in this class. We focus on simple medium. And of course, when we say linear, it means that your polarization density vector, here, is linearly proportional to electric field. When you apply an electric field, the response of this dipole is linear. Okay. If the response of this polarization is nonlinear, then we'll have this nonlinear term. But for this class, we drop this term, set it to be equal to 0. Okay. When I'm going to talk about nonlinear optics, we talk about linear optics in this class. And what is this polarization density vector? Well, if you go through the electromagnetic wave and also the electromagnetic one, you knew that the polarization density vector is you start to create some physical picture. You have a lot of electric dipoles. The polarization density vector is a lot of dipoles, and each dipole is given by this, if you still remember. And then you have this D, separation of D. If the distance is separated by D, and this positive charge, negative charge. And then you have a vector D from minus sign to plus sign. This is a one dipole. And then if you have many dipoles per unit volume, then you have this polarization density vector. This is the number of dipoles per unit volume. So think about this. You have small dipoles in this direction material, and then you add up all the dipole vector, the dipole vector, and then average over a volume. Then you have polarization density vector. And how is this generated? Well, look at this. You have an electric field to induce it. So polarization density vector must be proportional to the electric field, right? And electric field will depolarize the material. And if the relationship between P and E are linear, then we call this a linear material. Isotropic material means that this chi-E, the electric susceptibility, does not depend on the coordinate. Okay, this is just the constant, not a function of x, y, z. Okay, and not related to the direction of this electric field, basically. Okay, so and non-dispersive means that the response does not depend on the frequency. But later we're going to introduce dispersion into this expression. Okay, so for simple medium, it's a linear, isotropic, and non-dispersive material. And in this class, we'll be always talking about linear material. But then later in this class, we'll be talking about birefringence material and also dispersive material. Okay, so this is the concept that I want to introduce right now. All right, and if the electric field is very strong, sometimes there will be nonlinear term, but this term is going to be removed in our discussion for this class. And if you combine the mass equations, and you start to create such a wave equation, and now on the right hand side you have a lot of dipoles. Well, what is dipole? Dipole is the antenna. Okay, so this is the polarization density vector. This means that on your right hand side you have one antenna. You have some antenna producing radiation, and this radiation will propagate in space. Okay, and so on the right hand side you have a source, generate radiation, and the radiation is moving in space, governed by this wave equation. Right? Any question about this? So this is sort of a very quick review. And so if you want to understand the wave propagation, we need to look into this equation. Okay, this is the propagation of the radiation wave, and on the right hand side, this is the source of the excitation to produce this radiation. So think about that. On the right hand side, you have an antenna produce radiation, and then the wave will propagate in space. All right. So we need to look into antenna radiation pattern in the final chapter of the electromagnetic wave. You can plot the antenna pattern if you still remember since last semester when I taught the electromagnetic wave. This is the antenna pattern. So if you have a dipole oscillating like this, then you have an antenna pattern like this. There's no radiation along the oscillation direction, okay? And the strongest radiation is along this direction, okay? And if you cut it along this plane, antenna is along this direction, and then you cut it along this plane, then you don't have any structure in the radiation. You don't have any structure along this direction. Basically, it's just isotropic. But think about you have an antenna like this, and along this direction, well, the charge oscillates like this, and there's no radiation along this direction. Strongest radiation is along this direction. But then when you look around, just look down, then the radiation intensity along every direction are the same. Okay, because of symmetry. Okay, if you have an antenna block like this. So this is a radiation pattern, dipole radiation pattern, and this is the E plane, this is the H plane, the radiation pattern, if you still remember. Okay. All right. So if you use such a linear relationship, then in fact you can combine the polarization density term into this term. Okay, and once you combine the radiation in free space, of course, that you don't have anything, just the vacuum permeability and vacuum permittivity. But if you combine this, the polarization density term with this term, then you start to create a refractive index inside this term. Okay, because of the dipole response. Okay, if we go back to this. We go back to this expression. This P is equal to epsilon chi E electric field, and then so you have a portion of E minus mu not epsilon not double derivative of E with respect to time, and then on the right hand side you have mu not epsilon not chi E, and then you have the this double derivative of electric field on the right hand side. For now, I just dropped the vector, and then you combine these two terms together. Okay, you combine these two terms together, then you end up having portion E, portion E minus mu naught epsilon naught 1 plus chi E. And double derivative of E with respect to time. And this is the relative permittivity. Okay? And this is written into the square of the refractive index. Alright, so with this you can write this. Because this is equal to 1 over c naught square, the vacuum speed of light. Okay, and for this you have, this is going to be 1 over c square. This c is equal to c naught over refractive index. That's why you have this. Okay. Because this is the square of the refractive index. So you end up having, remember that this is 1 over c naught square. So this can be written down here divided by n squared, and c naught divided by n is equal to c. Okay, so you can go through this algebra easily. So you can organize the whole thing into a wave propagating in the material. When the wave, electromagnetic wave, propagates into a medium, the dipole produces radiation, and this radiation, in fact, will continue to produce a wave propagating inside material, but the radiation process somehow slows down the propagation speed of the light. So think about that. You have some cartoon in space. Okay, I'm walking inside some material, and I produce radiation, but the radiation generation process takes some time, so I get slowed down if I walk into some material. Okay, so it's not just the simple concept that a wave propagating inside material. The concept is that the wave enter the material and then pull the dipole, and the dipole produces radiation. And this radiation becomes slowed down because there's a radiation generation process. Okay, I hope that you can sort of picture the physical picture. Okay, so this is the sort of, well, if I go back this, I'd like to have the physical picture. If I come back here, it tells you that the radiation is generated by this dipole oscillation inside a material. But in fact, if you write it like this, you sort of combine the radiation generation process into the propagation process. But the net effect is that the propagation speed of the wave becomes slower. Okay, because it takes some time to excite the dipole, and it takes some time for the dipole to produce radiation. So the propagation speed of the wave inside material is slowed down. So whenever you talk about refractive index, now you understand this is the excitation and radiation process. So it means the coupling, the N is a coupling between the electric field and the dipole. If the coupling is very strong, this means that this N can be big. Okay. Can you catch the concept? I hope.
So what is dipole doing that? The wave is going through the material, dielectric material. What is the dipole doing?
Well, when electromagnetic wave entering dielectric material like this, the electric field is going to pull it, right? Well, originally the atom could be just like this. Okay, it's a cloud of electrons, and then with a positive ion inside. When electromagnetic wave entering the material, it's going to change into this. And for the electric field to change the distribution of the electrons like this, you generate dipole. Previously, you don't have dipole. And then the wave will generate this dipole. And once you generate this and then start the oscillation, you produce radiation. And it takes some time. Okay, it takes some time. And that is why the wave overall is slowed down. So you can create some physical picture for that.
But the incident wave is still the same, right? This one is taking time, but that wave is still there.
The waves still continue to well, think about that. I don't change myself. I enter some water. Okay, but when I'm in the water, you still see me, right? I'm still I. But then I have to slow down because I have to sort of fight through the water molecule. So the net effect is that you see me inside water, I'm going to move slower. But I don't change myself. But the water, in fact, will be changed because I sort of fight through the water molecule and walk inside. Okay. So this is the cartoon you can sort of generate in your brain and then start to understand why we talk about refractive index. So refractive index is a coupling of electric field between the dielectric materials. Okay, if the coupling is very strong, this means that the refractive index is going to be big. All right. So a wave is so interesting that it's governed by this wave equation. And now you understand quite well. The wave equation looks like this. And then because of the shape of the waveform, we can categorize the wave into spherical wave, cylindrical wave, and plane wave. 3 different kinds. Okay. And for plane wave, you're going to see waveform like this. It's just a plane in space without any variation. And this kind of wave does not diffract in space if there's no aperture or obstacles. Okay. And if the waveform is the cylindrical shape, for example, if you send a plane wave through a slit, it's going to generate this kind of cylindrical waveform. And we call this cylindrical wave. And the wave amplitude is going to have this dependence. And because of power conservation, I talk about this when I lectured the electromagnetic wave. You're going to have 1/square of R dependence for cylindrical wave. Okay. And I also talked about this last week because I'm still teaching the electromagnetic wave this semester. And if you have a spherical wave, then the general solution is going to have this form. with a 1/r dependence to conserve the total power. So this is the general solution for this wave equation. Okay. So we talk about the solutions of wave equation in XYZ coordinate system, in cylindrical coordinate system, and in spherical coordinate system. And because of the square of the amplitude is proportional to the intensity, to conserve the power, you have this R and square root of R dependence in those expressions. Because when you do an integration of the surface, the total power is going to be conserved for the lossless space. Okay. So this is sort of the concept I want to tell you. All right, and a time harmonic wave will have a sinusoidal variation of the amplitude. So think about that, you have such a general solution, and then you have sinusoidal wave. So basically you convert this sinusoidal function into the form of the general solution of the wave equation. And we call this wave function. Okay, this is wave function. And so for sinusoidal wave or time harmonic wave, then you write it into this form. And in this form, you knew that this is the angular frequency. And then this omega over u is going to give you a wave number. Okay, omega over u is going to give you the wave number. I go through this a little bit faster by assuming that you more or less went through this before. Okay, so you have this kind of the oscillation of the wave in space and also in time, and the phase velocity is the up in this expression. Because that when you set this phase to be constant, then you end up having phase velocity u that defines the propagation speed of the wavefront. Okay, the phase velocity basically is the wavefront velocity. So a wavefront is a constant phase plane. Okay, you just set this to be the constant, then you end up having z equal to constant given a constant time. Then you have this kind of wavefront, well-aligned wavefront with the surface normal along z direction. Okay. Then you can also calculate the periodicity in time and also periodicity in space. The periodicity in time, you take an inverse of the periodicity in time. You get frequency. You get frequency of the wave, and this is well known that the frequency multiplied with the spatial period, you get a phase velocity. Okay. So there are two important parameters you want to remember for wave. You have angular frequency, you have the wave number, and angular frequency is equal to 2 pi, the frequency in hertz. And this is equal to 2 pi over the temporal period of this wave, the temporal period. And this P is equal to 2 pi, the spatial period. And the spatial period is called wavelength. Okay. And there's a relationship between omega and K. That is the phase velocity. That is the phase velocity of the wave. So those are important things that you want to always remember when you deal with the electromagnetic wave. Okay. The temporal period, spatial period, and then the relationship gives you the phase velocity, the ratio gives you the phase velocity. But then, in general, you can propagate a wavefront along any arbitrary direction. Okay. Along any arbitrary direction. So this k vector could have 3 components. Okay, this k vector can have 3 components. All right, so you have Ks, Ky, Kz. This means that you can have phase velocity and also wavelengths along 3 different directions. And if you start with this r, a position vector, and set it to be a constant, then it's going to define a plane for your wavefront. Okay, if you do this dot product from the geometry that you learn in your high school, then k dot r equal to constant defines a plane that is away from in space. Okay, and that is why we call this a plane wave. Okay, so this is the sort of some quick review we have for the basic concept of electromagnetic wave. But this is the sort of basic understanding about wave. But then we want to create some mathematical skills for doing calculation. The first thing is that if you have a harmonic wave, this means that the temporal variation of the wave is already understood. Okay, so we can sort of extract the temporal variation into this term and leave the rest here. And this E naught is a function of position, and also the phase is called phasor. Okay, it's called a phasor. For electromagnetic wave, this phasor is also a function of position. So the basically a phasor is a part of this complex notation without the exponential j omega t. Okay, so whenever you have a harmonic field written into a cosine or sine dependence, and you write into a complex notation and take out this exponential j omega t, this product is called phasor. Okay, and with this construction, if this is already understood, and with this construction, then the calculation can become very easy, especially in the polar form. If you multiply 2 complex numbers together and write into the polar form, this means that I can do summation. So summation is relatively easier compared with multiplication and division, right? So this becomes an easy tool for you to do complex analysis. Yeah, for phasor notations, the calculation becomes easier, especially when you convert it into phasor notation, some similarity with a phase term. So this is the convenience of the calculation. And the temporal part is understood, so you can put it into the all sorts of calculations. For example, the differentiation of a real electric field in space, if this electric field is a harmonic function, if it can be understood with a harmonic function, I can do this. And in the end, you find that in fact this is just the phasor of the electric field multiplied with j omega, and then the rest does not change. Okay, so this means that I can sort of replace this with this if I just try to do phasor calculation, because this part is already understood. Okay, so this is why we adopt phasor calculations, because the temporal part can be just leaven out in the calculation. Well, remember that when we talk about this equation, the wave equation, this is tedious. Why? Because c is a function of position and time at the same time. This is tedious. This is sort of partial differential equation with respect to the space, and this is partial differential equation with respect to time. So you have 2 variables. This is tedious. But then let's try to remove the temporal part if we deal with a harmonic wave. Okay, we deal with a harmonic wave, and we write this the electric field. This is can be a function of time and space. And now you take out this temporal part for your calculation. Okay. So for the integration, if you do an integration of a real electric field, in the end, you basically just the phasor of the electric field divided by j omega, and then you have a term that is already understood. Okay, so if you sort of rewrite this into the phasor notation, the integration sign basically just give you 1 over j omega in the integration. Okay, so now we are in a position to convert this the wave equation into a phasor notation. Okay, the double derivative of this with respect to time just create this j omega square when you write this c into a phasor notation. Well, again, the reason we try to use a phasor notation is try to remove the temporal dependence from the calculation. If you have to deal with the spatial dependence and also temporal dependence at the same time, it's tedious. Okay, but when you convert this into a phasor notation, you only deal with spatial derivative. You forget the temporal dependence because that is understood. So once you have the phasor notation equation, we call Helmholtz equation, and then we obtain this solution. Then later we're going to convert this back to the real solution by multiplying this exponential j omega t. Okay, so this is the sort of mathematical tricks that allow you to do a quick calculation. So everything can start from this Helmholtz equation if you knew that you will be dealing with a harmonic field. Okay. All right. So now we sort of specify all the discussion with a harmonic field. Okay, with a harmonic field. Then we start from Helmholtz equation for the discussion. Okay. So this is the Helmholtz equation for the electric field, Helmholtz equation for the magnetic field, and then there's the relationship between k and omega. That is the ratio of omega over k is the speed of light. Is the calculation, and this k is 2 pi over lambda. All right. So the general solution for the electric field is given by the general solution of this the Helmholtz equation for the electric field is given by this one. Okay, this is just one of the solutions for a Helmholtz equation. There could be multiple solutions, but this one is particularly simple and easy to understand. So we extract it and take it out for discussion. Okay. So if you put this into Helmholtz equation, you end up having a requirement for this Ks, Ky, Kz. Okay. So this is how we discussed before when we talked about the electromagnetic wave. So you sort of put this trial solution into the Helmholtz equation, then you specify the Ks, Ky, Kz. And K has 3 components, and R is basically just a position vector in space. Okay. And so the compact form is to write into this. You write this K, write this K into some magnitude of it, and then a propagation direction, a unit vector, to specify the wavefront propagation direction. So basically this AN, this unit vector is K, divided by the magnitude of it. Okay. And this K, again, right here, is equal to 2 pi over lambda. Okay? Any question? No? So this is compact form. I repeat it here. All right, so we sort of use this expression. Well, the reason we can do this calculation is that we start from the Helmholtz equation. But always remember that when you start from the Helmholtz equation, it is already understood that the field is going to be a harmonic field. Okay, So think about that, you get a solution like this, and then you want to find the real electric field in space that you can measure. You multiply this, the solution of the Helmholtz equation with this exponential geometry, and take a real part of it to get the final result. Okay, so let's do it. Then if you do this calculation, you end up having some amplitude in front of it. And electric field is a vector, so you specify a direction, and then the argument is going to be equal to omega t minus k dot r plus some initial phase, because this E naught could be a complex number. Okay, this could be a complex number, and then this is understood for a harmonic field. Okay, so you finish this calculation, you end up having this expression. Okay, and of course you can spell out what k dot r is. K dot r, remember k has 3 components. Okay, k has 3 components along x, y, z direction. R is just a general position vector. Okay, so k dot r, if you just spell out the specific form of the k dot r, then you end up having this. Okay, and don't forget that this E can be a complex number, so there's an initial phase associated with it. You need to put it into this expression. Okay. Another question? All right. So now I want to give you this drawing so that you understand this is a plane wave. K dot r, well, the wavefront, how do you figure out a wavefront? You set the phase term to be a constant, because a wavefront is a constant phase plane. So you set the phase to be a constant. If you set the phase to be a constant, at any time, this can be a constant. You set this time, just stop your clock. Okay, and then k dot r is a constant. It's nothing more than a plane in space. Okay, and this is the geometric construction you understood already when you were in high school, right? K dot r is a constant. It means that you project r along this k direction, and it's always a constant. And the only possibility for this position vector is on a plane. Okay, so k dot r geometrically define a plane in space. And that's why we call this a plane wave. Okay, that's why we call this a plane wave. All right, so this is more or less the introduction to tell you what a plane wave is. And we start everything, I want to remind you that we start everything from Maxwell equations. And then we introduce the field affected by materials. So we have the reduced electric field in dielectric material and increased magnetic flux density in magnetic material. And then we introduce the dipole radiation concept. When you propagate a wave into a dielectric material, the electric field of the wave is going to pull the electric dipoles. And then that will slow down the propagation of the wave. And then we have the concept about refractive index. Then you might ask, why didn't we discuss magnetic dipole? Well, magnetic force, according to the Lorentz force equation, magnetic force will only be significant if the charge is moving. Okay. In a stationary material, the charge does not quite have a linear velocity. It's a random sort of thermal vibration and so on, but the charge does not have a high velocity. Okay, so we don't quite talk about magnetic dipole inside the material, but the electric dipole induced inside material basically will radiate, and the net effect is that the electric field, the electromagnetic wave gets slowed down inside the material. And then we introduce the harmonic wave, harmonic field, with the no oscillation of the wave in the time domain, like this sinusoidal oscillation. then we can use a simple mathematical tool to calculate the solutions. So we start from the Helmholtz equation, and then finally construct the solution, the plane wave solutions for the wave propagating in space. So this is pretty much I want to tell you today. And on Friday, this Friday, I will continue to finish this part of lecture. And then next week is going to be your participation in the presentations. And I hope that we will have a lot of discussions. So this is the sort of nature learning process. I hope you like it. Okay. So today, I'll finish up here. See you on Friday. Okay. I think we have the Friday class around 10 a.m. So I will see you here. Right.
Next